lines before to approximate function values. So whenever we use a tangent line, you've actually been creating a 1-degree or linear equation, obviously, right? It's a tangent line, right? But they're only close to the curves for a small section. So like in this example graph, I've graphed the curve y equals sine of x and the tangent line at pi over 3, right? So close to pi over 3, right? It's pretty close there. But right, the line gets pretty far away from the graph of sine of x. It's not super accurate anymore once we have, I'm just trying to get my zoom right, once we move too far away from pi over 3. So what this actually is this is actually a first degree Taylor polynomial. So every tangent line that you've ever created, you've actually been doing 1-degree Taylor polynomials without knowing it. So what we're going to do is we're going to expand these to have higher degrees, so like second, third, fourth, and so on degrees, and this is going to increase the accuracy of our approximations. So I have the same graph here, so we still have the tangent line at y equals sine of x, and we have that tangent line at pi over 3, but I've also graphed the 3rd degree Taylor polynomial at pi over 3. That's that green curve, and you can see how close that green curve is to the original red graph for much longer than the blue tangent line, right? The blue tangent line starts to separate around here, right? And the green graph goes all the way like over here before it really gets far away from the sine curve, right? So we have a much wider interval of accuracy in approximations when we're trying to like figure out different values of the original function, maybe without a calculator. So we're going to go over what these are and then how to make them, and I'll show you how to use them on the calculator too. Right, so a Taylor polynomial, the definition of a Taylor polynomial is if a function f of x has n derivatives, which means that you can take like 2, 3, 4, whatever value of n you need derivatives. Then the polynomial degree n, so this n matches the number of derivatives you're taking, and that's going to be the degree of your Taylor polynomial, is equal to the function evaluated at c plus the first derivative at c times, oh, that's a typo. This should be an x minus c, plus the second derivative at c times x minus c squared over 2 factorial, plus the third derivative at c times x minus c cubed over 3 factorial. Hopefully you're starting to see the pattern emerge, plus all the way out to the nth derivative of c times x minus c to the n over n factorial, right? So if we're looking at this, right, the degree of the derivative, right, whatever derivative you're taking, matches the degree of the exponent on your x minus c, and it matches the factorial in the denominator. And we call this the Taylor polynomial of degree n for f of x at x equaling c. And this is where, right, so the polynomial is centered, we say, at x equaling c. So in other words, that's the point of tangency. That's the point where it's definitely going to have the same value as the original function. So then we also have these things called Maclaurin polynomials, and they're exactly the same thing except that they're always centered at c equaling 0. So Maclaurin polynomial is just a special case of a Taylor polynomial, but they do have 2 different names. And that's just because they're named after 2 different mathematicians. Right, so who came up with this stuff, right? If you want to go ahead and read this, you can go ahead and pause the video and read through this. It's just a little bit of history about Brooke Taylor and Colin Maclaurin, the 2 mathematicians kind of behind these, and for why like they give different credit to different people. They're kind of cool people, so you can go ahead and pause this if you want to read through that. So let's actually get into some of the math. So suppose that f is a function with continuous derivatives, and we're given these values. F of 2 is 3, f prime of 2 is 4. That's an equal sign, not a minus sign. Man, I got all sorts of typos in here today. Second derivative at 2 is 7, and the third derivative at 2 is negative 5. And we're going to use those values to write the 3rd degree Taylor polynomial for f at x equaling 2. So when we see 3rd degree Taylor polynomial, that means that I should see x minus c cubed as the very last term. So the first thing we're going to do is we're just going to kind of set up that little formula. So we're going to say that this is P3 of x. Some people use P3 for polynomials. Some people will use a capital T since it's a Taylor polynomial. You can really use whatever you want unless the problem tells you what to use. This is the notation that I usually use for doing a Taylor polynomial, and then the subscript tells you what degree you're using. So our c value is 2, so that's our center point. So a Taylor polynomial goes f of 2, in this case, or f of c, plus the first derivative at our c value, so f prime of 2, times x minus c, so x minus 2 in this case, right, technically to the first power and over 1 factorial, but those are, not essential to write because they're just ones. Then we do plus the second derivative at c times x minus c squared all over 2 factorial. And then we have a third degree, so we're going to take it out to f prime, triple prime of 2 times x minus 2 cubed all over 3 factorial. Okay, so P3 of x, I should say. Right, so f of 2 is 3. F prime of 2 is 4, so we get 4 times x minus 2. F double prime is 7 times x minus 2 squared. If you want, you can leave it as 2 factorial, or 2 factorial is 2 times 1, so that's 2. And then normally it would be a plus, but in this case, the third derivative at 2 is negative, so I'm going to put negative 5 times x minus 2 cubed all over 3 factorial, but that is just 3 times 2 times 1, or 6. And that's it. That's our Taylor polynomial. Right, so pretty easy, especially because they gave us all the values. Obviously, you know how to take derivatives and plug in numbers, so you can evaluate for those values as well. So let's actually go ahead and do something like that. So we're going to go ahead and find the 5th degree Taylor polynomial for the natural log centered at x equaling 1, and then we're going to use that polynomial to approximate the natural log of 1.1. And then we'll use our calculator to kind of see how accurate we are. Okay, so 5th degree. So I like to kind of use a table. I don't actually draw the table lines, but I kind of organize it like a chart. So, right, I got y equals the natural, oops, I just realized I zoomed in too far. Now you guys can't see. Okay, we'll just, nope, okay, there we go. Y is the natural log of x. Okay, and if I do y of 1, that's the natural log of 1, or 0. Pretty easy there. Okay, so then I got y. Would help if I also wrote the problem correctly. There we go. Okay, so the first derivative is 1 over x, right, which is just x to the negative first. And then y prime of 1, right, that's 1 over 1, so I get 1. Okay, so my second derivative, using the power rule, is going to be negative 1 x to the negative 2, right, or negative 1 over x squared. And then my second derivative at 1 is going to be negative 1 over 1 squared, so I get negative 1. Right? Third derivative is going to be 2x to the negative 3, right, or 2 over x cubed. So my third derivative at 1 is going to be 2 over 1 cubed, so that's going to give me 2. Right, remember when we get to the fourth derivative, we use this parenthesis notation as our exponent. So the fourth derivative is going to be negative 6x to the negative fourth, or negative 6 over x to the fourth. So if I plug in 1, I'm going to get negative 6. And then, all right, I need a 5th degree, so I need my 5th derivative. So using power rule again, I get 24x to the negative 5th, right? So 24 over x to the 5th. So my 5th derivative is going to be positive 24. So now that we're going to go ahead and put all of this together, my P5 of x is going to be 0 plus my first derivative times x minus c, so x minus 1. Right. I'm going to actually go ahead and write this up top just so I have a straight line area to put it in. Okay, so plus my second derivative, so that case this is a minus, so I get 1 times x minus 1 squared all over 2 factorial. And then I'm going to put out my third degree term, so that's going to be plus 2 times x minus 1 cubed over 3 factorial minus 6 times x minus 1 to the fourth over 4 factorial plus 24 times x minus 1 to the fifth over 5 factorial. Now, if you wanted to simplify it, you totally could, right? So that 0 term in the front, you don't need to write that anymore. And then if you know your factorials, this actually comes out pretty nicely. So we have x minus 1 minus x minus 1 squared over 2. Right? And then 3 factorial is 6, but 2 over 6 is 1/3. So I'm going to get x minus 1 cubed over 3. 4 factorial is 6 times 4, so that's 24, right? And then that's actually going to cancel out to be 1/4. So I'm going to get x minus 1 to the 4th over 4 plus 5 factorial is 120, and 24 goes into 125 times actually, so that's actually going to reduce to x minus 1 to the 5th. Oops. All over 5. So the cool thing about the natural log is a lot of the factorials will actually cancel out. You can see that we have like a denominator of 1 technically here, right? And then it just alternates signs, and then the denominators just increase and match the power perfectly. So let's go ahead and use this to approximate the natural log of 1.1. So P5 of 1.1, we're just going to plug in 1.1, and it seems silly to do that without a calculator, so let's go ahead and do our calculator. So let's see, I have 1.1 minus 1 plus my fraction of, oops, and it was a minus in between, so we're going to go back and fix that. So 1.1 minus 1 all squared, all divided by 2. And then we have plus the same thing, so put another fraction in here. 1.1 minus 1, right, cubed. Of course, you could just be putting 0.1 in these. That's totally fine. I'm just going to type it exactly as I would write it first. And then we're just going to keep adding on our terms. You just want to be careful that you don't make any typos, because this is a lot to type, and then having to go back through and find it again if you make a mistake would be awful. Okay, last fraction. We got 1.1 minus 1 raised to the 5th all over 5. Just going to double check my signs are in there correctly. They look like they are. So we get that our approximation is 0.095. So that's not bad. So 0.095. And if we look at the actual value of ln of 1.1, go back to our calculator real fast, just type in natural log 1.1. Let's see how close we are. Oh, hey, look. They match all the way out to this decimal value before there's any break. That's pretty close accuracy, so we're actually not that bad. We're not that far off. So we're going to do one more problem here. Okay. So this problem's going to have 3 parts to it. So we're going to look at a Maclaurin series. We're going to find a 6-degree Maclaurin series for cosine of x. We're going to use that polynomial to approximate cosine of 1, and then we're going to find the error between our approximation and the actual value. So I'm going to zoom in. So 6th degree of, there we go, I'm just going to move the screen over, of cosine of x. Okay, so I got f of x is cosine of x. And it's a Maclaurin series, which means I am centering it at 0. So f of 0, cosine of 0 is 1. Okay, derivative, and I'm actually going to drop my of x notation after this, right? That's negative sine. Okay, f prime of 0, so sine of 0 is 0. Right. Double prime of x, it's going to be negative cosine of x. So second derivative value at cosine of 0 is going to be negative 1 there. Right, my third derivative is going to be positive sine, right? We know that sine of 0 is 0. So the nice thing about these trig functions is that they alternate with the zeros a lot if you're using these like values where they like the 90-degree marks. Okay, so fourth derivative would then be cosine of x. Okay, so that derivative value is going to repeat back to the beginning again. Right, so because these are circular functions, we're just repeating our values. Then we need a 6th degree, so taking it out to my 6th term for my derivatives, it's going to be negative cosine of x, so my 6th derivative at 0 is going to be negative 1. Okay, so P6, right, is my first function value plus, I'm just going to write out all the terms, so x minus, well, we don't have to do x minus 0 squared, do we? We're just going to do times x, right, so that's going to cancel out, right, and then we're going to do minus for that second derivative value here, so that's 1 times x squared over 2 factorial plus 0 times x cubed over 3 factorial, so we know that's also going to go away. That was our third derivative, so fourth derivative was 1, so times x to the fourth over 4 factorial plus 0 x to the fifth over 5 factorial, and I realize you cannot see what I'm writing right now, so we're going to slide that over. Actually, let's just zoom out a little bit. There we go. So that's also going to zero out, and then our sixth derivative was a minus 1, so we're going to have 1 times x to the sixth over 6 factorial. So if we condense this, because every other term cancels out, we actually get 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. Okay, let's go out a little bit. Okay, so we are going to use that polynomial to approximate cosine of 1. So cosine of 1 is going to be approximately p6 of 1. And then all we're going to do is type that into our handy-dandy calculator. So we're going to go over here and just type that in. So I'm going to get 1 minus 1 squared, which is just 1, over 2 factorial, which is 2. Okay, plus alpha y equals 1 to the fourth, so that's going to be 1 again. 4 factorial, right, that's going to be 24, but if you don't know those off the top of your head, right, you're just going to type in 4 and go to math, over to probability, and it's option 4. Then minus, and then I have 1 to the 6th, so 1 again, and then over 6 factorial. You can also get the factorial symbol by going alpha, I think it's window. Yep, and it's option number 9. So you can get that as well. So my calculator is giving to me as a fraction, so I'm going to write down the fraction, 389 over 720. And if I want it as a decimal, math option 2, right, which is about 0.540. Okay, so not a bad approximation, right? So I have those written down, and then what is the approximate error? So the error is the absolute value, right, of the actual minus your approximation, right? So the order doesn't really matter because you're taking the absolute value. So my actual, so if we go over to my calculator again, I'm going to go to math number for absolute value. I'm going to type in cosine of 1, and then I'm going to subtract my answer for my error. Right, and look at how small that is. That's 2.423. I'm sorry, 2.453. I don't know why I can't read today. Times 10 to the negative fifth. That's a really small error. So that means we're essentially like totally accurate with this. It's a really close error, right? So I'm going to write that down as 2.453 times 10 to the negative fifth. So super small, right? If you wanted to, you could write that as 1, 2, 3, 4 zeros, and then 2, 4, 3. Yep, so if we look at it there we go. That's how you make a Taylor and a Maclaurin polynomial.